Hi, my name is John-Michael Colef, and I will be doing problem 2 of homework 3. Okay, so problem 2 gives us the probability density function, little f, and they give us y equals g of x, where g of x is absolute value. So, of x, for x between negative 1 and 1, and 0 otherwise. So I drew that here. G of x is absolute value of x between negative 1 and 0 elsewhere. Little f of x, I drew over here. This is the probability density function. Now, part 1 wants you to find the probability density function fy of y. And part 2 wants you to find the probability distribution function big Fy. So I'm going to find the big F first. So, big F of y is equal to the probability that random variable y is less than y. Now, if we take a look here, this only happens for when y is greater than or equal to 0. So when y is greater than or equal to 0, then random variable y will be less than or equal to y. So there are two cases that we have to consider. So we have the probability that the absolute value of x is less than or equal to y. Or we also have the case where random variable y is equal to 0. Because in that case, y and random variable y are equal, which is part of this probability. So we have to consider that. So, continuing here, this becomes probability negative y less than or equal to x, random variable. Or, now, when is random variable y equal to 0? That's when x is greater than 1 or less than negative 1. So we have or random variable x greater than 1 or random variable x less than negative 1. Now, because these three events are mutually exclusive, we can write this. So this is what we have. Now, we have to consider each of these. So we write, this becomes capital F of x at y minus capital F of x at minus y, plus this is just 1 minus the integral from negative infinity to 1 of little f of x dx, and this guy becomes the integral from negative infinity to negative 1 of f of x dx. Now, if we take a look at this guy, little f of x is 0 before negative 1. So this integral just goes to 0. All we have to consider are these. So, we have this guy becomes the integral from negative 1 to y. Now, it should be from negative infinity to y, but I put negative 1 because we have the step function, which takes care of everything from to the left of negative 1. So we have e to the minus x plus 1 dx. Ignore this. Minus negative 1 to negative y. Same reasoning, because the step function takes care of that. And we have this plus 1 minus this integral here, which is from minus 1 to 1 also, because the step function takes care of everything to the left of minus 1. E to the minus x plus 1 dx. So we get minus e to the minus y plus 1 plus 1 plus e to the y minus 1 minus 1 plus 1 plus e to the minus 2 minus 1. And this just comes from doing the integration. So the integral of this guy is just negative e, e to the same thing, evaluated between negative 1 and between negative 1 and y. So we have the y and then the plus 1 is a negative 1. And the same thing for these guys. It's just doing the integrals. So we cancel this with this and this with this. So we're left with this guy plus this guy. So, right. So this is capital Fy of y. Well, actually, let me be careful. Capital Fy of y. This is true. This is capital Fy of y for y greater than 0. So let me write it that way because that's more correct. That's a minus 2 for y greater than 0. Now, as we said before, for y less than 0, if y is over here, there is no random variable y underneath that or equal to that. So, for y less than 0, we get 0. Now, for y greater than 1, anything is underneath this. So, we'll always get an answer, so the probability is 1 for y greater than 1. So this is the full answer. Now, let's draw what this looks like. So, we have our axis here. So, at 0, when you plug in 0, we get e to the minus 2, which is, I'm going to make this 1, by the way. It's much less than 1. So, at 0, we get some point over here. So, there's a jump here. Because everything after 0, before 0 is 0. So we have this point here, which is e to the minus 2. Now, I'm going to evaluate at 1. So at 1, what happens? Come back here. We get minus e to the minus 2 plus 1 plus e to the minus 2. These goes away and you just get 1. So at 1, you get 1. And then for y greater than 1, we still have 1. So it continues like this. In between, it goes exponentially up like this. So I'm just putting the little arrow, the little dotted lines here. But the actual function is this, the one I'm tracing right here. So this is big F of y. Now, for the second part, actually it was the first part, I did them out of order. But anyway, little f of y is actually just the derivative of big F. dy. So, let's go back here and take the derivative. So the derivative of this guy, we just get rid of the minuses, so let me just put my brackets. We get rid of the minuses, so we get e to the minus y plus 1. This is a constant, goes to 0, and then this is just 1 times this, so we just get the same thing back. And this is also for y greater than 0. For y less than 0, derivative of 0, 0, so we get this for y less than 0. For y greater than 1, again, 0. Derivative of a constant, 0. But now we have to be careful. Because there was this discontinuity here, the derivative of the discontinuity is a delta function. And the delta function of weight, e to the minus 2. So at y equals 0, we have e to the minus 2 delta of x, of y. Sorry. So what does this look like? Let us draw. So at y equals 0, we have delta function of weight e to the minus 2. But also at y equals 0, we have 2 times e to the minus 1, which is lower than, I'll call this 1, so it's somewhere lower than 1, it's like over here somewhere. And then at 1, we actually get, if we plug in 1, we get 1 plus e to the minus 2. So it's somewhere up here, something like somewhere up here. We get 1 plus e to the minus 2. By the way, this is 1, and this is here. So at 1, we get this point over here. So the way the function looks is something like this. So it goes like this, and down here. And then at 0, we have the discontinuity, which is taken care of by the delta function. So that, by the way, that's the weight of the delta function. So this is the function and the picture, and that completes problem 2.